session of the first week of the conference. Maybe on behalf of the people, I know the conference is not over, but on behalf of the people that, like me, are not able to attend the second week, I wanted to extend my and our thanks to the organizer. And I hope the first week was great. I'm sure the second week will be great, and I'm sure there'll be thank again on the second week and at the conclusion of the conference. But I wanted to thank them again, or well, thank them the first time for this great conference and this great half of the conference. Thank you. And without further ado, it's an honor to present Jérôme Buzzi from Orsay, who will talk to us about strong positive recurrence for diffeomorphisms.
Thank you. So I would like also to thank the organizers for this conference and for this opportunity to present this joint work with Sylvain CROVISIER and Omri SARIG. So let us explain what it is about. So okay, so the motivating result that will appear soon is a result about exponential mixing for the measure of maximal entropy. Okay, now it's on. So okay, so I will first start by stating our basic result, which is about quantitative mixing for the measures of maximal entropy of smooth surface diffeomorphisms. Okay, then what we will enter what from our point of view is the real subject, that is a new notion of non-uniform hyperbolicity. So a new notion of what can it mean to be beyond uniform hyperbolicity. This is the SPR property, which I am here to advertise. We'll see that when we have this property, it implies a lot of statistical properties. It gives information about their measures of maximal entropy. So I will try, if time allows, to give some ideas of the proofs, so which will split into two parts. The first question is, how do you establish this property for all smooth surface diffeomorphism with positive entropy? And the second part, which is once you have this property, and you only then need C2, and you could be in any dimension, how do you get the statistical property from SPR? Okay, so let's start. So, okay, so in general, we will be considering a diffeomorphism of a closed manifold in any dimension with some regularity. You can also always assume that it is at least C1 plus holder, let's say C2. Okay, we have in mind the variational principle, and we will be focusing on measures that maximize the entropy, or MMEs, and in particular, the ergodic one. Okay, when the smoothness is C infinity, there is a classical result by Newhouse that tells you that such measures do exist. Okay, and in a previous work inside this project, we proved with Sylvain and Omri that on surfaces with positive topological entropy, you have finitely many MMEs. And if you assume topological transitivity, then you have exactly one. Okay, and so one of our motivating result is the following theorem. So for C infinity smooth surface diffeomorphism with positive topological entropy that are topologically mixing, so that by our previous result, we know that there is a unique MME, which is strongly mixing in the sense of ergodic theory. Then the new result is that actually it is exponentially mixing for Holder function. Okay, that's the definition. If you fix the exponent of the Holder continuity, then you have a rate, this kappa, an exponential rate that tells you how fast the correlation function converge to zero. It's an upper bound. Okay, so convergence to zero is just mixing, I mean, the strong mixing in the sense of ergodic theory. And here the exponential mixing is when you have such a rate. Okay, so that's what we that's what we are going to get, so that then I can bother you with this SPR notion. So the goal of the talk is to introduce this notion, a notion of hyperbolicity, which is sufficiently relaxed compared to a uniform hyperbolicity, so that we get many more things, but which is not so relaxed as to lose exponential mixing, and let's say for now, this kind of spectral gap properties. I mean, properties usually associated with a spectral gap when you have the chance to have an operator. Yes? Well, okay, the short answer is I don't know. If what is clear is that we say we do not see measures with zero entropy. Okay, so this is what I can say. And of course, well, you can be, well, so under the assumption of topological mixing, I don't know exactly what you may have if the entropy is zero. I don't know if it's possible. Yes. Yes. Okay, so what we know is that in general, if you remove the topological mixing or even topological transitivity assumption, what you have is that you may have several measures. Each measure may have a period, okay, which is some integer that you can compute by considering some periodic orbits. And up to that period, you have exponential mixing. Okay, this is just to, so here the topological mixing assumption is just to have a clear-cut statement and not get into this thing. So thank you. I mean, feel free to ask, of course. Okay, so now that's one of our goals, and then I want to convince you that the definition I will give is somewhat natural. Okay, so for this we go back to the non-uniform hyperbolicity in the sense of Pearson theory. So you have this diffeomorphism with, let's say, C1 plus something, C1, let's say C2 on any closed manifold, any dimension. You look at the invariant Borel probability measures. Often I assume ergodicity. So then you look at the Lyapunov exponents. So you can start with the Lyapunov spectrum, which is just a set of possible growth rate of vectors under the differential. Corresponding to that, you have the oscillated spaces, which are the subspaces where you see exactly one given growth, and when you ask it for both future and past. And this defines the Lyapunov exponent with the multiplicity being given by the dimension of the associated oscillated space. Okay, so you have these pointwise quantities. If you have an ergodic measure, then it's easy to see that these quantities are being invariant must be almost everywhere constant. So you can define all this notion for an ergodic measure. When you don't have an ergodic measure, for the Lyapunov exponent, for instance, you can just look at the average. Okay, so being hyperbolic in the sense of Pearson theory, is to have a measure, an invariant measure, for which almost everywhere there is no zero Lyapunov exponent. Okay, and hyperbolic of saddle type is if additionally you have some positive and some negative exponent. I mean, you have both signs are present. So key observation that I think was made first by Katok is that in the setting of surfaces, the invertible, then Ruel's inequality implies that positive entropy of a measure by itself, of an ergodic measure, by itself gives you hyperbolicity, and in fact, hyperbolicity of saddle type of that measure. Okay, just because the Ruel tells you that the entropy is bounded by the sum of positive exponent. So of course, if the sum of positive exponent, if the entropy is not zero, it tells you that there is some positive exponent. Since you are looking at diffeomorphism, you can look at the inverse. And when you apply Ruel inequality to the inverse, you get that there is some negative Lyapunov exponent. And now you say, oh, but I am in dimension 2, so I have only 2 exponents. So I have 1. Okay, that's so it looks, it's very easy once you know Ruel inequality, but it's fundamental to a lot of things that go on in dimension 2, or I mean for surfaces in dimension 2. And we can be a little bit more precise than saying that we have a hyperbolic measure of saddle type. Actually, it bounds the Lyapunov exponents away from 0. Okay, so this is completely classical. So that's hyperbolicity on the level of exponent of just the differential. Now in piercing theory, you want to control what's going on near orbits. Okay, so you or rather piercing introduced the piercing blocks. Okay, what are the piercing blocks? These are our points belong, so you need some parameters. You need an exponent, chi. You need some small number, epsilon, and a big constant, c. Okay, and then the piercing block defined by these constants is the set of points for which you can find a splitting, such that in the first factor of the splitting, you have exponential contraction in the future, and in the second one, you have exponential contraction in the past. Okay, these are uniform. Okay, and then you ask something more, which is if you move along the orbit, then you get the same type of behavior, except that the constant is allowed to grow a little bit. This is this factor exponential epsilon absolute value of k. So essentially, this is what. So it's a uniform hyperbolic set, which is not invariant. Okay, you can think it is almost invariant in the sense that if you push it by the dynamics or its inverse, you end up in the similar set with usually a slightly larger constant. Okay, so being in this set means that you have this exponential behavior uniform given by C and T, and then you have this slow possible decay of the constant given by epsilon. Okay, and then just so it's an exercise to check that if you have an invariant subset, which is contained, or let's say compact invariant subset, which is contained in some piercing block, if and only if it is actually a uniformly hyperbolic set. Okay, so it's really uniform hyperbolicity, but without the invariance, with something which is near invariance, but not exactly. Okay, so that's from the point of view of hyperbolic set. And then one of the first steps of piercing theory is to see that if you have a measure whose exponents are bounded away from 0 by chi, strictly, then the measure sees those sets. Okay, given the measure, you have to pick chi, so chi should be smaller then the absolute value of any exponent. And then you can take any epsilon as small as you wish. Then if you take a constant C big enough, then this Pearson block, captures a measure arbitrarily close to 1. Okay, and why did Pearson introduce the set? Because these sets, I mean, they carry some kind of uniform hyperbolicity, and in particular, for reasonable parameters, I mean, epsilon has to be small, then Pearson actually could build the stable and unstable Pearson manifold. Okay, and over these sets, they depend continuously on the base point. So it's really like a uniform. It's in fact a uniform hyperbolic situation, but without the invariance. Any question about that? Okay, so now let's go for our SPR property. So same setting. I just copied the definition of a Pearson block from the previous slide. And now I can state our new notion. I will say that a diffeomorphism in any dimension is strongly positively recurrent, or SPR, if there is, okay, let me say it in a simplified way first. So if there is a Pearson block that is seen by all measures with big entropy. Okay, now let's look at the details. The condition is that we have to be able to find chi, which is something like an exponent. Okay, and then for this chi, we want that for any epsilon is the decay along orbits, we can find a lower bound on the entropy, a big constant, a positive number tau, such that for any measure, any ergodic measure, so you see in Pearson lemma, we had for a given measure, we could find a constant large enough. Here, what we are saying is that we should be able to do that in a uniform way for all ergodic measures with entropy close to the maximum, close to the topological entropy. That's the, okay, and there we don't care whether the measure is close to 1, we just ask it to be bounded away from 0. Okay, and then if we have this property, so if we have this, if we forget a little bit about epsilon, this Pearson set that is seen uniformly by all measures with entropy large enough, then we say we have an SPR diffeomorphism. So, okay, I don't know if I succeeded in making you believe that this is a natural notion. Okay, what we, the first part is the first result is to say that, okay, you take a C-infinity smooth diffeomorphism on a closed surface. Then if the topological entropy is non-zero, you have this SPR property. Okay, so that's the, and now how do we get the statement I gave at the beginning? Well, we say that if you have a C1 plus alpha diffeomorphism on a closed manifold in any dimension, if it happens to be SPR, if you know that it is SPR for some reason, like the case we just stated before, then you will have exponential mixing for Holder function. Yes? Yes? Yeah, when you fix the constants, I mean, chi, epsilon, and the constant C, yeah, on this, you really have continuity, I think, in the CR compact open topology. Anyway, you are in a position where you can build local, stable, and unstable manifold of a definite size. No, here we don't assume it. What would happen is that, of course, since epsilon is chosen small, in fact, smaller than chi, it's enough. The these E subspaces E and F have to be invariant. Okay, so it can be, you can imagine examples. Well, just take the disjoint union of two anodes with different indices. Then it can happen that, okay, you need to take both a subset of both parts, and then so in some sense, then you would like to split. Okay, now if you want to capture all measures with large entropy, maybe you have to take a piecing block in two. Well, actually, if it's two anodes, you have to take the two pieces if they are equal entropy. Okay, so yeah, in some sense, you can certainly split any placing block according to the dimension. In our definition, you might need, in some cases, to keep all these pieces or several pieces. Okay, so we had this SPR property. We showed, or we claimed for now, that surface diffeomorphism with positive topological entropy have this SPR property. And now we say that the SPR property, now in any dimension and just small regularity, it does imply all, so first the exponential mixing, and then actually more or less all the statistical properties known to me. Okay, that is, so to make, so this is the statement. You take an MME, suppose that it is strongly mixing to avoid complications. Then for Holder continuous function, you have, so what I would expect, that is central limit theorem with a characterization of when the variance, the asymptotic variance vanishes, large deviations, comparison with the Brownian motion, this almost sure invariance principle, and then all many consequences of that. Okay, and just as I said, I'm assuming that there is no period to have a simple statement, but okay, I could be annoying. Questions? Okay, so now let's, so the first type of consequence of the SPR property was this these statistical properties. Now you have another group of properties which are about the existence finiteness of MMEs. So if you happen to know that a diffeomorphism is SPR with positive topological entropy, then it implies that it has some MME, which in small regularity is not given. So the SPR property implies existence. It also implies finiteness. So of course, so we proved it for in the case of infinity smooth surface diffeomorphism. Actually, this gives a slightly different proof. I mean, the basic notion involved in the proof turned out at the end to be the same, but it avoids some of the use of topological of the topology of the plane that was underlying our analysis in the previous thing. Okay, so if you use the statement about continuity of Lyapunov exponent for surface diffeomorphism that I give, then you know that they are SPR, and because of SPR, you have this. You know also through this way the finiteness of the number of MME. Yes? Okay, so it's more complicated. So for instance, you have these partially hyperbolic in dimension 3, which are circle extension. Okay, and then there is this result of Rodriguez, Hertz, Federico, and Hannah, Ali, Tazibi, and Aulures, that tell you that you have the rigid case where you essentially extend by rotations. And then there is you assume accessibility. Okay, so certainly they are topologically transitive. Anything I don't. Okay, Alice, thank you to say yes. Okay, but nevertheless, in the generic open and dense case, which is when it's hyperbolic, you have two measures. You have several measures, at least two. What happened? And yeah, so let's say that in dimension 2, there is a nice way to split the dynamics, at least up to things of zero entropy. Okay, this is what we did in the first paper. When you go to higher dimension, you lose this connection. First, you lose it. I mean, you cannot prove it. And actually, there are a counterexample to what you could imagine. I mean, if you, at least what I could imagine. So it doesn't turn out to be the right notion. Okay, there is a notion which works, seems to work much better, but is more abstract, which is the notion of Borel homoclinic classes. Okay, which actually was first, which is a generalization of Newhouse result, which appeared, for instance, in the work of so the two Rodriguez Hertzes, Ali and Ures, I think, about uniqueness of SRB measure on surfaces when you are topologically transitive. So there is we use this notion for a variant of it, I mean, in our paper, and this is the notion that works well in any dimension. Also, you get uniqueness on each of those pieces, and here to get the finite number, what you show is that since on the Pearson set you have uniform size of the stable and unstable manifold, okay, you cannot have infinitely many homoclinic classes. They have to, if you had infinitely many, they would intersect. So that's the proof in 5 seconds. Okay, so this we recover. So for surface diffeomorphism, this is not new, but the proof is a little bit different. Okay, so now still about the MME, we have this result about okay, so we know, let me say it like this. So assuming if you have a unique MME, then if you are C infinity, you have by the Newhouse essentially, well, by Newhouse, you have upper semi-continuity of the entropy map. Here I am assuming C infinity. So if you have a unique MME, then it's an exercise, I don't know, in the basic topology to see that if you have measures whose entropy converge to the topological entropy, they must converge to the unique MME. Okay, here what we have for the SPR property can be understood as a quantitative version of it. It is called effective intrinsic ergodicity. It tells you that, okay, weak convergence is that the averages of all continuous functions converge to the averages for the MME. And here there is a bound, which is by this square root of the difference of the topology of the entropy. Okay, and this was proved for subshift of finite type by Kadyrov not so long ago, and extended by Rohr and SARIG for let's say non-compact subshift of finite type, which are underlying our results actually. Okay, so you see we had this continuity of Lyapunov. Okay, let me just. Okay, so now let's look at this story about Lyapunov exponent. So I just reproduced the definition that I gave before. I just add the sum of positive exponent, this function unstable Jacobian. And now we can characterize the SPR property for, let's say, C1 plus alpha diffeomorphism of a closed manifold in any dimension in this way, that okay, there is no H, sorry. There is a chi, a positive number chi, such that if you have a sequence of ergodic measures with entropy converge to the topological entropy, okay, let's say that it also converge weakly to some measure mu, then what you want is that this measure mu, which is not necessarily ergodic, still all its ergodic components have the same index, okay, the same multiplicity of positive exponents and then of negative exponent. And more or less, their exponents are bounded away from zero by this fixed number chi. Okay, so this is one. So you are Piécine hyperbolic. Mu is hyperbolic in the sense of Piécine. It is actually chi hyperbolic and with a fixed index. I mean, the index is fixed over the different possible ergodic component of mu. If you take another sequence of mu k and you get another limit, then you are allowed to have a different index, but they should not mix. And now you ask that the unstable Jacobian, so the sum of the positive exponents for the measure mu k, you want it to converge to that of mu. You're limiting. So you have a convergence of the entropies and a convergence in weak star topology. Okay, the Lyapunov exponents are not in general averages of a continuous function. So you can have problem. You ask that you do not have problem. So you ask that the sum of the positive exponent converge to that sum for the limiting measure. Okay, and what the theorem says is that this is exactly SPR property. Okay, and so now once you have these properties, this characterization, you can apply it to surface diffeomorphism. First, the upper semi-continuity when you are C infinity tells you that any limiting measure mu that you obtain in this way will have full entropy. Now, let's say the Katok trick based on real inequality tells you that this measure mu is indeed chi hyperbolic of saddle type. Okay, and so you get this. You could take chi equal to h top over 2 if you like. Okay, and the index has no choice here since we are in dimension 2. And for surfaces, so in the non-trivial case, from our point of view, you have one positive Lyapunov exponent. So the sum of positive Lyapunov exponent is just a complicated way to say the positive exponent, the positive exponent. So this is the result that we had. And this is how we prove what I announced, that the SPR property holds for these smooth surface diffeomorphism. Okay, so if you here for now, I ask you to believe that. Okay, if you believe that, then it's a corollary of this result about continuity of Lyapunov exponent that we proved for this reason. Okay, this was our motivation for the analysis of this continuity property. Yeah, so now let me just rephrase the previous characterization by specializing to surfaces. Okay, then for surfaces, by the remark that we made, I mean, this Katok trick, we can forget about the first condition. Okay, then the index is no longer an issue. And we see that on surfaces, you are SPR exactly when the Lyapunov exponent converge to the exponent of the measure. Okay, so now it happens that, okay, we had the intrinsic the effective intrinsic ergodicity before. Okay, actually, it turns out that not only we can control the averages of order continuous function, but in some sense, it also extends to the Lyapunov exponent. And we are for a surface. And now what we get is that if it is okay, sorry, it is SPR. Yeah, so that's okay. Okay, this is so if you are in a surface, you just have to be C1 plus alpha. Then you have here I'm assuming a unique MME. Then you will have so okay. If you are SPR, you have this quantitative convergence of the Lyapunov exponent bounded by the entropy. And okay, we like this because it's a kind of rigidity result, since it tells you that for surfaces, if you have continuity of the Lyapunov exponent, in the sense that if you have a sequence of ergodic measure whose entropy converges to the topological entropy, then you have convergence to the exponent of the MME. Then, in fact, this convergence has to be quantitative. I mean, this square root appears. So, okay, so now, very good. So now I will try to explain why, how do we get the SPR property from the convergence of the sum of the positive exponent. Okay, so for this, we use the projective extension of the dynamics. So we have M is our manifold. You can think of it as a surface. Well, you should think of it as a surface. Sorry, I wrote it in the case of surfaces. Then, okay, so then you have the projective dynamic, which is F hat is just, okay, you extend F by its derivative, its differential. And you have the dilation, this function phi hat, defined on the projective bundle. In the obvious way, it is the logarithm of the derivative of F along the direction. Of course, the projective bundle, you not only have a point, but you have a direction. So you can define the expansion as a continuous function. Okay, and let's consider an invariant measure, which is of hyperbolic of saddle type. So almost everywhere you have a positive and a negative exponent. Okay, and now you want to find a Pearson block such that the measure mu will see it as soon as its entropy is big enough. Okay, to satisfy the SPR property. Okay, and along the way we will use the convergence of the positive exponent, the top exponent. So okay, so first we need to understand how measures can lift. Okay, so the basic result is that if we have an ergodic measure mu on the surface, then we can lift it to the projective bundle in two ergodic ways exactly. One is the unstable lift, where you just push on the unstable space given by Orsay-Ledet's theorem. So you get an isomorphic measure, a first isomorphic measure. And you can also push to the graph of the stable oscillated space, okay, the one associated to the negative exponent, and you get another one, okay, and you can show that there is, very classical things, there are no other ergodic lift if you start it from an ergodic measure. Okay, if you start from something which is not ergodic, things are a little bit complicated, but if mu is a hyperbolic of saddle time that is almost everywhere, no zero Lyapunov exponent, one positive, one negative exponent, no zero exponent, then essentially what happens is that if you look at the ergodic decomposition, this mu here, okay, and for each ergodic component, you apply the previous result and you get some mixing. And for each component, you can choose measurably how much you want of the unstable versus the stable lift. Okay, and now the big property of this, sorry, it got mixed. This was, yeah, okay, it's true also here. The top Lyapunov exponent for the measure on the surface is just the average of the dilation for the unstable lift of this measure. And same thing for the bottom Lyapunov exponent, the negative Lyapunov exponent. Okay, so you started for some things which are given by Orsay-Ledet's theorem. You lift to the projective bundle, and there, my recall, you only need to ask Birkhoff. Okay, so now something is going to happen. Now we use the continuity of the Lyapunov exponent. Okay, and what I claim is that the continuity of the Lyapunov exponent implies, in fact, it is equivalent to the following fact on the projective bundle, which is that, okay, you have, okay, let me do it here. So you want to consider the limit of the Lyapunov exponent. So by what I said, okay, first I use that this is just the average for the unstable lift of the dilation function. Now I say, oh, but that's an average of a continuous function. I have convergence in the weak star topology. Okay, so this is just this, okay, where mu hat is the weak star limit of the lifts. Okay, here it's an unstable lift. Here I don't know. Okay, the question is what is mu hat? Okay, now so our assumption is that by Newhouse, mu, the limiting measure has full topological entropy. Okay, now the entropy of mu is just the average of the entropy of its ergodic component. Okay, and now what we are, but this can only be achieved if almost all ergodic components are MMEs. So in particular, they are hyperbolic of saddle type. So I can apply the fact number 2, I think, that tells me, okay, the limits of the unstable lift has to be of this form. So I forgot where I put the okay, one moment. For some measurable function A, okay, and now what you apply this to the dilation function. So this will be the positive exponent. of mu xi. The negative exponent, sorry, okay, let's keep the notations. The negative exponent of mu xi. Okay, you have this. So now you have the average of the top exponent of the ergodic component. This is by definition the top Lyapunov exponent of mu. Okay, minus what? Minus this. Okay, and now the assumption of, now I use that I have continuity of the Lyapunov exponent, that this limit is actually the top Lyapunov exponent of the limiting measure. Okay, and from this, I get that, well, this should be 0. Okay, but what I have here is, this is strictly positive, since I know that this is always bigger than the entropy or equal. This is less than minus the entropy. So this is really, well, at least like 2 times the topological entropy. So therefore, what I see is that the function A is 0 almost everywhere. But saying that the function A is 0 almost everywhere just tells me that indeed mu hat, the limit of the unstable lift, is itself an unstable lift. Okay, so that's what I wanted to. Now that once you have this, what you can do, well, what do? You apply Orsay-Ledet's theorem. Okay, Orsay-Ledet's theorem tells you that for each measure which has an exponent bigger than something, then the strictly bigger than chi, or here I choose chi equal to half the topological entropy. Doesn't really matter. Okay, for each measure, I get an iterate such that I will see this expansion for the unstable direction after that iterate. Okay, and then I can formulate it in the terms of an open set. Okay, but I can arrange to have 0 a measure boundary. And so then it's not only true for one measure, but for any measure from a weak star neighborhood of that measure. Okay, so in this way, I can deal with the ergodic decomposition itself, and I can find that just so I can prove this fourth step, which tells me that, okay, if you give me some positive number alpha, I can find a threshold on the entropy and an iterate, which will be valid for all measures with entropy bigger than the threshold. That is, I will have this expansion, this kind of uniform expansion for on a set of measure almost equal to 1. Okay, and here I'm formulating something for the measure on the surface, but it comes from the fact that I have these measures, the lift. Okay, that the lift, that mu hat is an unstable lift, and this is, if I want to, now I don't really have the time, but if I wanted to be more precise about the argument in step 4, I have to put mu hat in it. Okay, it is mu hat that sees an open set with big measure, and therefore it sees it because it is the unstable lift of mu. Okay, and now we know that this unstable lift is the limit of the mu k hat. Therefore, this mu k hat also sees the same open set with a big measure, and this is exactly, this gives us inequality that is given. Okay, so it tells us that there is a uniform expansion almost all the time, and from this you can deduce that you have a pièce in block which has big measure for all the measures that satisfied the previous thing. Okay, it involved, as usual, Fliss lemma and construction typical of Pearson theory. You want to go from something arbitrary to a tempered thing. I don't have the time to enter in it. Okay, and this gives you I hope I have given you some idea about how you use continuity of the Lyapunov exponent, at least in dimension 2 for surface diffeomorphism, to get to the SPR property. That is the fact that all measures with big entropy see some good Pearson block, okay, some set with some kind of uniform hyperbolicity. Okay, I'm not. So how do we prove the statistical properties? I want how many minutes do I have? Is it positive? Not really. Okay, so I just want to say that, okay, the SPR property for diffeomorphism that is new was introduced because there is a more or less classical property for Markov shifts, which are symbolic dynamics, which is underlying this, and if you know that measures C are given Pearson block, it will tell you that the measures that you lift on this symbolic dynamics see a finite number of symbols with positive probability. Okay, and this is one of the characterizations of the SPR property for Markov shifts. And now that you know that the coding is SPR in this old sense, okay, there are lots of results that gives you a lot of statistical properties. And sometimes you have to work a little bit to be exactly in the same setting. I don't want to get into that. As you see, there are many names of many corresponding to many works that we are relying on. Okay, but this way we get that the SPR property for diffeomorphism gives us let's say, the previous SPR property for Markov shift, and this gives us the statistical properties. Okay, so this is what I tried to say. Okay, so what I can say is that we are dealing with the MME. We think it's not, well, we think it's complicated enough, but we think that it should go through with this no really new ID for equilibrium measures for Holder continuous potentials. Okay, a key question is about the SRB measure. So where the potential is minus log of the unstable Jacobian. So it is not Holder continuous on the surface or on the manifold. And here there is a real difficulty. Another question is what happens when you have only finite smoothness. Okay, in Yomdin type result, you have this threshold of log of the expansion divided by the regularity. Okay, our techniques are not optimal at all with respect to that. So we could produce some results, but which are not very nice. David Burguet has developed a stronger tool that may achieve this sharp bound. Okay, so we didn't. Okay, so we have this SPR notion. It contains this class of smooth surface diffeomorphism with positive entropy. What about higher dimensions? Okay, it's not true in general. There are some interesting classes, but okay, most things remain to be done. Okay, so we use symbolic dynamics. Okay, nowadays I'm told that young people prefer anisotropic Hilbert spaces, so they are welcome to find one. Okay, thank you.
Questions or comments?
So if a priori in some setting you know that you have measure of maximal entropy,
Yes.
is it too relaxed? Just ask for this SPR condition for MME and not for all of the high entropy measures, or it is really essential?
Well, yeah, you're right that the statistical properties are just about the measures, whereas the SPR property are about measures which are almost MMEs. So, yeah, I don't know. I mean, the only answer that I can give you is the obvious one, that our techniques involves showing that this SPR property for the coding, okay, SPR is also, stands also, I mean, when it was introduced by Gurevich, I think he called it stably positive recurrence because it's also related to stable. So yeah, it's probably, I mean, the answer is probably that you're right, that there are some situations where one could think that one could hope that the MME is, I don't know, exponentially mixing without having this property. What you have to be aware, though, is that in the symbolic setting, okay, you have this paper by Buzzi and Omri SARIG that tell you that in some sense, well, it's not only exponential mixing, okay? They have a spectral gap for a specific kind of Hilbert space. So yeah, it's more than, and then if you have this stronger property, they show that you must be the Markov shift must be SPR in the classical sense. So there is some space, but it's not so big.
Questions or comments? Well, if not, let's thank our speaker again. And